All right. So any other questions, comments, concerns, anything like that before we get started? Let me put the hand out. Okay. All right. Doesn't look like there's any questions yet. So let's just get into it. So first thing is first, let's review really briefly what we did last time. So last time we did alkylation. That one was pretty straightforward. And then we did the acetoacetic ester synthesis. And now we're going to do the malonic ester synthesis. And that's pretty much exactly the same. There's only a few tiny differences. So let's review that real quick. So essentially, in this first step, we performed an alkylation. In the second step, we did an acyl substitution. And then in the third step, we did a decarboxylation. We also talked about how this is an acetoacetic ester. And one other thing that I want to mention is we said that this guy's name is acetoacetic ester, but I don't believe I mentioned what the more general name for these types of molecules are. So this one specifically is an acetoacetic ester because this has the acetone group, and then this is an acetic ester. So do you guys have any guesses or any idea what you think this type of molecule would be called? Something that has a ketone and an ester beta to one another. Someone said a beta dicarbonyl ester. That's kind of close, actually. So we're going to call it, I'm going to write it in the corner here. If it looks, I'm sorry, Bear's being stupid in the background. All right, so if it looks like so, any kind of R group, we're going to call this a beta keto ester. So the general name of this is a beta keto ester. And the most common one that we usually see is this acetoacetic ester. I'll scroll so you guys can see that for a second. And then a malonic ester, oh, sorry. Someone said, would beta keto ester be the IUPAC name? So kind of like, it's kind of like the common name. Like we call something a carboxylic acid, but then you have to name each carboxylic acid based on like how many carbons and stuff there are. So you would just replace it with whatever kind of ketone you have with whatever kind of ester you have. But for the purposes of this class, if you just call it a beta keto ester, that's good enough. That's specific enough for what Dr. West wants. So for this next one, we said that this guy is a malonic ester. If we go to the side, we can also say that if it looks like so, it is a beta diester. Okay, so now that we got the naming stuff out of the way, let's go ahead and do the mechanism. So we have these reagents. We said that if we have this here, what is it going to act like? It has a negative charge. OET minus. Yes, it will act like a base, and specifically, this one has a name. What do we call that kind of base? The alkoxide, exactly. Okay, cool. We can also call it ethoxide. That's also true. So the base is going to come in, and steal a beta hydrogen. And in this case, we actually only have one beta hydrogen to choose from. So not only is this like the most acidic position on the molecule, there's nowhere else we could take a hydrogen from. So they made it super easy for us. So these electrons come in, steal the hydrogen, give those electrons back to our carbon. So we end up with and I know this is a big molecule, it's going to take up a lot of space, but that's okay. All right, so now that we have a negative charge on the carbon, what intermediate name does this have? That was a weird way of saying that. What can we name this intermediate? Yes, the enolate. Awesome. All right, so at this point, we have this alkyl halide in solution. So what kind of reaction are we going to do next? Super basic stuff. Yes, an SN2-like reaction, exactly. So we're going to come in, attack, kick off the leaving group. Don't forget that this carbon here exists. So we're going to go ahead and redraw it as so we still have this hydrogen here, and we have the little bend, and we have a pH. I don't want to draw it out, so I'm just going to write it as pH. All right, and at this point, we have made A. Any questions up until this point? All right, doesn't look like it. So now we're reacting with NaOH. So when we have NaOH in the last reaction, what kind of mechanism did we undergo? Yes, exactly right. We underwent a hydrolysis where we, more specifically, did a nucleophilic acyl substitution, or I should say more generally, we had a nucleophilic acyl substitution, and we substituted the ester. In this case, we have two esters. So what do you guys think is going to happen? Are we going to substitute the left, the right, both, neither? What do you think? Okay, cool. Someone said either. Someone said doesn't matter. Someone said both. Okay, so you guys are right. It doesn't matter. They're both exactly the same. But we're not just going to replace one of them because we have no way of making this more selective. So we actually have to replace both. So just for the sake of like having the arrows, I'm going to draw it like this. All right, there we go. So when we replace both of those, we go from having two esters to having two whats? Carboxylic acids. Perfect. All right. So at this point, we have B. And someone please remind me what heat is going to do, because we have heat in our next step. What kind of mechanism is heat going to cause? Yes, a decarboxylation, exactly. So let's go ahead and do that. Someone made a really good point and said we have to rotate something. That's absolutely correct. So if you guys remember, I said we need something specific, or we need two specific things in order to do a decarboxylation. Does anyone remember what those were? Heat and a carboxylic acid. True, exactly. So you need heat. You also need the carbonyls to be beta to one another. And you also need one of these to be a carboxylic acid. So I'm going to write a little star here. And I'm going to say we need at least one carboxylic acid. And the carbonyls must be beta. So that's very, very important for you guys to remember. In this case, we have 2 carboxylic acids, but that's okay. As long as we have at least one, we're good. So I'm going to choose to rotate this one, even though it doesn't really matter. They're both the same. And so what is the point of rotating? What are we trying to rotate? So when I rotate this bond, what will be pointing up and what will be pointing down? The OH will go up, exactly. So what has to be pointing down? The carbonyl. Awesome. Okay, cool. So I know we only went over this once, so it might be a little hard to remember. But what is the first step of decarboxylation? What is going to happen with this hydrogen? So yes, the carbonyl is going to grab the hydrogen. We have a special word for that kind of bond. Do you guys remember? A hydrogen bond, exactly. So the first step of decarboxylation is actually going to be hydrogen bonding. So the hydrogen is going to grab, or hydrogen is going to be stolen by the oxygen. So we're going to use these electrons to make a bond. And so when we do that, this bond has to be broken. And those electrons are going to go over here and create a double bond. And so that means this bond right here has to be broken. And those electrons are going to jump over here to create another double bond. So it's almost kind of sort of like a Friedel-Crafts reaction, right? When it's all happening at once. What do we call that kind of reaction? When all the bonds are made and broken at the same time. Exactly, yes, it's a concerted reaction, which just means that all the bonds are being broken and made at the same time. Perfect. So we are actually going to get 2 different products. Does anyone remember what our side product is? Or our byproduct that we don't really care about? CO2, exactly. So we have our CO2 in the background. We don't care about him. Oh, my bad. I don't know why I did that. And then the product that we actually do care about is going to look like so. We now have a single bond to the oxygen. I'm also going to draw our phenyl going up and our hydrogen pointing down. And we have a double bond right here. And we have a bond to hydrogen. So, what kind of molecule is this? What kind of functional group? Yes, this is the enol. It looks kind of weird because of the little OH here, but we're going to still call this the enol. And we know that if there's acid or base around, what can happen to the enol? It can undergo what? Tautomerization. Perfect. So I'm going to draw that with purple arrows. And so we know the tautomer for this would be drawn as so. We know we're going to have our carbonyl reformed. We're going to have a single bond here. We bring this hydrogen back down. And this group is going to stay the same. So this is no longer a ketone enol pair. It's a it's a carboxylic acid enol pair. But that's just a minor detail. It's not like going to destroy your reaction. Just keep in mind that there's still tautomers, and this is still going to be the enol, and we can tautomerize at the end because we have acid or base left in the reaction. I feel like we went through that kind of quick, or maybe time is just moving weird in my head. How do you guys feel about that? Are we okay? Any questions? Good. Okay, cool. How I would go about it, kind of like the short rosemary version. And I saw the comment in the chat. I'll get to that once again. But so how I would do it, like the short way, is I would just see, okay, cool, we have the acidic alpha hydrogen right here. I know that this is going to be an alkylation. So go ahead and add whatever alkyl halide we have here. And then we know NaOH, swap that for an OH. And then heat. You're probably going to have to draw out the decarboxylation a couple times. I know I had to. But eventually, once you draw it out a bunch of times, you can tell that you're just going to kick off this whole thing and end up with a double bond here and an H here. But we're going to do some practice with that because you definitely have to do this a couple times before you can kind of see the shortcut way. Okay, so someone had asked what does the tautomerization produce? So basically the product here will be this guy, but we know that the enol can tautomerize because we have some catalyst left in solution. And so the tautomerization will occur and you can get the carboxylic acid form or you can get the enol form. And then someone had asked, why would the second hydrogen be put back on the carbon in the keto form? So basically, the whole thing for tautomerization is you pick up the hydrogen and you move it around. So in this case, it was the green hydrogen. You're just going to pick it up and put it here so that you can get rid of the double bond here. So it's almost like we're pushing these electrons up here, which creates a plus charge here. And that plus charge is satisfied by this hydrogen. And yes, the ketone form is, or the keto, I should say, form is usually more stable and more favorable. So we're just going to call this the keto form or the carboxylic acid form. You can call it either. The reason we call it that is because usually in the tautomeric pairs that we've done, it's the keto and enol forms. Bear, please stop. I swear, Bear is fine. He just likes to cry in the background. Okay, so before... You know what? Let's do some of these questions first. Another important thing that we talked about, but we didn't answer these questions in the handout, so I want to do them real quick, When we're talking about acidity, we've done this a couple times throughout the semester as we learned different concepts. And so let me highlight this hydrogen, this one, and this one. We know that when we're looking for acidity, we know that the hydrogen attached to the oxygen is going to be the most acidic. So A is going to be the most acidic. And then we know that all of these are attached to carbons. So the next thing we look at is what? Think about cardio. So none of them have a charge. This one is attached to oxygen. These are attached to carbons. Next thing we look at is resonance. Absolutely. So of these guys, we know that a triple bond, relatively speaking, has more resonance than a double bond or a single bond. But when compared to these allylic positions, do we think that the triple bond will be more or less acidic? So will the triple bond be more or less acidic than the, oh, wow, you guys already got it. So yes, triple bond is going to be less acidic than the allylic position. So we're going to put B all the way over here in last place. And then when we're comparing C versus D, we know that the one with the most resonance is going to be the most acidic. So which one do we think is more acidic, C or D? C, yes, and it's because it's stabilized by 2 carbonyls versus just 1 carbonyl. So this would be the order. And he likes to give you some big molecule like this to scare you and then ask you which one is the most acidic hydrogen. So we can cancel, or first of all, we see that we see that all of these choices are on carbon. So there's no oxygens, they're all on a carbon. So we're going to skip right over to resonance. And we can see that there's no resonance here. We get rid of that. And then instead of going like one by one through every single one, like doing like A, B, C, D, whatever, how I like to do it is narrow it down automatically to allylic and benzylic positions. So in this case, we have A, and I'm going to say that's allylic. B is both benzylic and allylic. C is allylic times 2. And F is allylic. So between these, we see that we have a benzylic and allylic, and then we have one that's 2 times the allylic because there's 2 carbonyls. So I'm going to get rid of A and F. Between B and C, which one do you think will be more acidic? B, exactly. So I'm going to write it here. Oh. B will be the most acidic because it's on 2 allylic positions and the benzylic position. So it's super, super stabilized. Any questions about acidity? Okay, so we've done all of this stuff. We're going to do this question. It's in the handout. I believe it's like page 4 or 5, page 4. And then someone asked about which one would be the least acidic. Let's look at it. So the least acidic would be E because it's on a primary carbon and there's no resonance whatsoever. All right, so let's do this reaction. And this is a really great example because it uses something called LDA. Does anyone know what LDA is? And you don't have to give me like super specifics. Just in general. Yes, awesome. It is a strong base. And someone said specifically it is a strong, bulky base, and that is correct. So it looks like so. And the reason it's important for us to know that it's bulky is because it kind of has a special property, if we want to call it that. So essentially, we always talk about how we have 2 alpha positions, and I'm only drawing 1 hydrogen for the second position, but you guys know there's 3. So alpha 1 and alpha 2. And usually, we prefer which position? Alpha 1, yes, because we know that it's more substituted. It's going to make a more favorable double bond. So for that reason, it's more preferable to steal this hydrogen and then do whatever we want to do. But in this case, since we have such a big, bulky base, it has to go to the least sterically hindered side. So in this reaction, we're actually going to use these electrons to steal this hydrogen right here and give those electrons back to the carbon. So in the case of LDA as our base, that's pretty much going to be the only time where we are going to favor the less stable carbon, or the less stable alpha carbon, I should say. Also, I think I forgot to send the attendance sheet, so I'm going to send that in the chat, and you guys can fill it out whenever you have a second. All right. So the second step of this reaction has this OTS group. What is OTS? Do you guys have any idea? It's kind of a new, weird-looking thing. It's a protecting group, and it's tosylate. Yes, exactly. So tosylate is a protecting group, but it can also be something else. I believe we did 1 or 2 examples like this. Yes, it can be a really good leaving group. Exactly. So I'm going to go ahead and just call this whole thing a leaving group. So that means here we have a C2H5, which is just this. And attached to that, we are going to just replace OTS with leaving group. So in the next step, we made the enolate on the less substituted carbon right here. And so that is going to attack this and do what kind of mechanism? Yep, an SN2-like mechanism. So we're going to kick off the leaving group. And we get... And remember, this is not like chapter 17. We're not replacing this carbon. We're adding to it. So we're going to go ahead and add 1, 2 carbons. And which of these answer choices looks familiar? A, exactly. So if we didn't really know how to exactly do this reaction, how could we work through the answer choices? Well, first things first, we never learned a reaction like this where we're adding to the beta carbon, right? So that's a terrible answer. This one, yeah, sorry. This one, I can see where you would get tripped up because it's adding to the more substituted carbon. The way we cancel this out is because we see LDA. We know automatically you have to add to the less substituted side. So because of this, it's out. For D, it just completely got rid of the whole carbonyl and it didn't add anything. So we know that's wrong. That's gross. And then here, what kind of product is this? Or what does it almost look like they tried to do? Yeah, it's almost like they either tried to do a Williamson ether synthesis or like maybe the acetal ketol reaction. Like they did some weird thing here, right? And we know that no matter what we do, we're not going to replace the carbonyl with an alcohol. So we're going to cancel that out. So you'd really be tied between A and C, but we know that it's a bulky base, so we're going to pick A. Any questions? Okay, I'm going to start scrolling, but you guys please feel free to ask questions as you have them. Okay. So the next question is, which of these halides is predicted to alkylate malonic ester as the anion in the highest yield? Whoa, those are a lot of words, right? So essentially, all it's saying is, which of the following will undergo the malonic ester reaction, and we want to alkylate, and we want the highest yield. So you guys should be thinking about the malonic ester synthesis. And we know that we do what kind of reaction mechanism? An SN2-like mechanism, sweet. And for that kind of mechanism, do we want more or less bulky? Less, exactly. So which one of these is the least bulky? A, exactly. Perfect answer. That is correct. So did you guys kind of follow how I thought through it, or do you want to go through it one more time? And then someone asked, if we were given the benzylic option, would we choose that over the methyl? For the purposes of this class, I don't think he'll give you both options, but you want the least bulky, so I would still go with methyl, even though I know there is some stuff about the benzylic position. And yes, I can go through it one more time. And then someone asked a great question, and it was, what if it was the acetoacidic ester synthesis? So it would actually be exactly the same logic behind it. So we would get the same answer. So how we got this answer in the first place is we know that it's asking for the malonic ester synthesis. And most specifically, it wants the alkylation step. And it wants the highest yield. So we're thinking about trying to find the best answer to make the alkylation go like the fastest and as high yield as possible. And so we know that in the alkylation, we're going to have some kind of base on top that will deprotonate. And we know that we will have some kind of alkyl halide. And so when we attack the alkyl halide, we know it's an SN2 mechanism. And so since we have that SN2, we want to choose the least bulky to make this go fastest. And so the least bulky would be A. Make sense? A little bit? I'm just going to scroll down really quick just to see what else is left of this page. Okay, cool. All right, so if you guys have any questions on that, obviously you can ask me, but we're just going to scroll down to this last one of this handout. So the question is, which of the following can undergo decarboxylation? So please remind me, what do we need in order to undergo decarboxylation? Yes, we need at least one carboxylic acid. And we need the carbonyls to be beta. Perfect, perfect, perfect. So the first thing that we notice is this one's beta. This one is not beta. What's their relationship? Alpha, exactly. So these are alpha to one another. This is out. For C, those are for sure not beta. It's actually going to be alpha, beta, gamma, delta. So that is way off. So now we're stuck with A and D because those are the only beta options. Which one do we think is correct? Cool, everyone said D, and why do we think it's D? Because of the carboxylic acid. Perfect. So this one is ketones on both sides. Has to be wrong. This one is beta, and it has our OH. Oh, yes. And so for C, someone asked how we went from like alpha, beta, gamma, delta. So this is going to be named pretty much the same way that it is for lactones. So the order goes alpha, beta, gamma, delta. And so we start here at the carbonyl. 1 carbon away is our alpha. 2 will be beta. 3 will be gamma. And then so the next carbonyl is on 1 position next to the gamma. So that's the delta. And that's going to be the relationship. They're going to be delta to one another. Does that make more sense? Okay, cool. Alrighty, awesome. So we finished chapter 18. Yay. And I want to spend the rest of the session going over practice problems so we can kind of summarize and wrap up chapter 18. So I forgot to ask if you guys were done with that. I apologize, but I'll go back to it if you guys need. So I'm just going into the, what is it called? The practice problems that you guys have on Canvas. And I'm going to go ahead and go to where chapter 18 starts. And that will be right here. And then one person asked, are we doing chapter 19 on Friday? Yeah, so I thought we might have time for it today, but I think it's better if we just practice chapter 18 today. So we'll do chapter 19 on Friday. And then I will be posting Monday's SI sessions. I will post them today along with today's SI sessions. I was just having some trouble with my laptop. And then someone asked for his practice exam, is it really worth 1 point? I don't think so. I think it's worth 10 points. And I think he just made a typo because when you click on the assignment, it says 10 points. but he hasn't clarified that yet, so I don't know for sure. Someone said it's 10 points when you submit it, so there we go. Alrighty, so which of the following is a keto-enol tautomeric pair? What do you guys think? You guys, gals, and all my other pals. I believe it's graded for accuracy, not completion. That's what someone asked. So, yes, I think you guys are right. It will be answer choice B. And the reason is when we go between a ketone and an enol, we know obviously ketone, and then we know that that will turn into an OH, and we will end up with a double bond attached to the alpha carbon. And so B is the only one who matches that description. Going on to the next one. I don't know if you guys were able to. Are we good? I think we are. Alrighty. So please tell me what is required for a racimization reaction. Yes, we need a chiral alpha carbon, and we do need an alpha hydrogen to be present there. Exactly. So we want chiral alpha carbon and an alpha hydrogen. Sweet. So automatically we can kick off this one because we have two benzene rings. We can't have chirality. Which other one can we automatically kick out if we look closely? Number 4, exactly, because all of these groups are the same. No chirality. This one is just here to trick you. Now between 2 and 3, we see that this is definitely chiral. This is definitely chiral. But 2 does not have a hydrogen. Exactly. It just has 3 carbon groups. So our answer is going to be C, which is this one. Any questions on this one? Okay. I don't know why that page is there in the middle. Whatever. So we are looking for this reaction, and it doesn't tell us what reaction this is, so we have to figure it out. We have OH minus and Cl2. What kind of mechanism are we going to do? Halogenation. Perfect. All right. So we're doing halogenation in base. So we know that we're going to fully substitute the most favorable alpha position. And so between alpha 1 and alpha 2, which one are we going to choose? Which one's the most favorable? Okay, so most people said 2. A couple people said 1. So why is alpha 1 kind of a trick? Because there's no hydrogens. Exactly. This double bond means that we have no hydrogens here. So we have to pick alpha 2. So I'll just draw an arrow. This is where we are going to add. And how many hydrogens do we have there? Only 1. So we know that we only have the opportunity to add 1 chlorine since we only had 1 hydrogen available. Right? So we know that this is our answer. And which choice matches that? Choice 2, aka B, you are correct. So if you didn't know how to do that, let's look through the answer choices and kind of think about it. So first of all, this guy sticks out to me. Why in the world would we add to the benzene ring? We don't want to do that. That's not favorable. Ew. Get rid of it. Next thing we see is this one and this one added to the beta position. And even more than that, this dude added an OH. Where would we get that from? No. Ew. We don't want that. We also know that this is incorrect because we can't add anything to the beta position. And then just what the heck, right? Like, why would we do that? What? No. Ew. Gross. Trash. So we know that 2 is correct. And even if we had to kind of work backward, sorry about that, we still know that B is the only one that makes sense. Any questions about how I did this one? All right, this one is already solved, and we're going to end it with this one, just because we made a big deal about the first one being in base. This one is actually in acid. So the difference is in acid, we can only substitute one time. But in this case, there is going to be no difference between the acid and base catalyst because we only have one hydrogen anyway. So we still get this as our answer. I just wanted to compare and contrast the acid and base in this case. Do you guys have any questions, comments, or concerns at all? Someone asked, do I know how many questions are on the practice final? Apparently, according to everyone, it's 59. Thank you guys for jumping in and answering that. I really appreciate that. And then someone asked, if there were 2 hydrogens, would we only substitute once? Exactly. You are correct. Yes, we would do that. So let's say this was also a hydrogen, right? And let's zoom out and bring both of those into it. So if we had an extra hydrogen here instead of a carbon, in the base, we would add 2 chlorines. But in the acid, we would still only add 1 chlorine. So we would have that. You're very welcome. I hope that kind of makes sense. Just to not confuse anyone. All right. And yes, someone said it goes really fast. I know. Did he give you guys the full 2 hours to take it? The practice final? Or wait, did it even come as a quiz, or did you just get a packet? I forget. He gave us a piece. Okay. So never mind. That's really weird how he chose to do it, but I guess it makes the most sense that way. Yeah, so what people are saying is that you have to submit a quiz, but he gave you a PDF. So I don't really know how it works, to be completely honest. I just know that usually you have to do a Scantron, but obviously we can't do that this semester, so. Oh, you guys can't see me. I shrugged. Oh, just kidding. So I was wrong. Someone said you actually have to download the PDF, put your answers on the PDF, and then upload that into the quiz. So that makes much more sense. Thank you for that. All right. So any other questions or anything before I let y'all go? Oh, yes, and that is true. He made an announcement today, so I might as well repeat that for you guys. Remember that the practice final is due tomorrow at noon. So it's not at midnight. So please don't get that mixed up, because I know that's probably going to be a problem for some people. And someone asked me to go back to the chapter 18 handout, so yes, I can do that. Alrighty, so that's all I have for you guys. If you have any more questions, I'll be here for another minute or so. But I hope you guys have a great day. And I will see you Friday. And yes, I can just go through. You're very welcome. Have a great day, guys. Oh, you guys can't see me waving either. It's okay. Bye.